Our next speaker is Dr. Clement Wann. He is also a former student of Professor Chen-Ming Hu. Dr. Wann is the Director, Advanced Transistor Research Division of TSMC. Prior to joining TSMC, he worked at IBM. In 1996, Dr. Wann received his PhD in EE with Professor Chen-Ming Hu. So let's welcome Dr. Wann.
Good morning. I'm honored to introduce this topic titled "The FinFET Takeover," and I would it could have took over earlier, a few years back, because when Chen-Ming started this program. Actually, I worked with Professor Hu from 1990 till 1996. The Berkeley FinFET program, I think, officially started after that. And then I went to, but I think I can contribute to some part of it is the incubation time, I would call that, some preparation. And after that, I went to IBM in Yorktown Heights. As a matter of fact, at that time, I was working on the competing transistors. So therefore, I think I get to the other aspect. And I was telling Philip, there's a reason this talk is delayed a little bit, because then I can cite the person who worked on the competing architecture, and myself involved in that as well. And then later, Professor Hu started this program in TSMC. As I said, that this actually, we could have started, be the first to introduce FinFET technologies. That didn't happen, and I joined TSMC in 2007. So I was trying to, well, actually before that, I was pretty much become a manufacturing person. I was ramping some processors. So when I get back to TSMC, then people asked me to look at some of these early transistor development work. And so I did some reflection, and so I actually include some of the reflection in today's talk. And so it's also kind of a little bit biased to my personal view, and also from maybe from a little bit of TSMC's view. But I think it was some of these things are really pretty much into the very heated discussed in the panel session in IEDM. But I hold my opinions back because I want to share with this audience. This is for the first time I'll share these are some of my thoughts on these topics about that the FinFET takeover, and also a tribute to Chen-Ming. I should do some introductions for, I think there's some audience which may not be familiar with the FinFET, but the way to look at this is that you have a planar transistor, and then your planar transistor, then you put your finger, just kind of grab it and pull it up, and that make it a fin. It's the structure-wise, just something like that. So you have a planar device, now you stand up. Then if you need to adjust for a different width, then you just put several fins, and that's how you adjust the drive strength. Once the transistor, you start to fold the channel, and there are several options. I use this one just to show that you can look at this, that in the old planar structure, you have you can in the planar section, I use 3 colors, blue, red, and green, and you can fold it and you stand up. And so the first thing people look at is that, wow, then you can make the transistor smaller. So you can squeeze the transistor into a smaller width. And this is one thought that we can use these transistors. Then this is kind of an area savings. But actually, most people, as it turns out, interested is that to use this transistor on the right-hand side is that you keep it. You even make the width larger, that's okay. But then you use it to reduce the VDD, and so that to save power. And that's how FinFETs work. But actually, it'll work both ways. So this is the picture, and the only picture I'm going to show, which has had these kind of real structure. Well, I think there's a couple of reasons. First, I'm under some limitation. I'm not able to share some of this picture with you. And secondly, I'm pretty sure that if I start to talk about how we implement this structure, it may sound interesting at first. You'll get very, very bored. We just talked about how you make sure that you etch these things right, you fill these things right. So that's not what I'm going to focus today, but just to kind of give you a feel about how this structure look like. Okay, I'm going to provide a little bit of a theory aspect of the FinFET takeover things behind this. And so this is based on my last student assignment from Clement, and there was a paper, a comparative study of advanced MOS concept. And I worked with, at that time, we were very blessed under Professor Hu's influence. We have Kenji Noda of NEC, Tetsu Tanaka of Fujitsu, Makoto Yoshida of Hitachi. And so they all brought their transistor structures. So I have a privilege to work with them to study these transistors. And so the key concept we came up at that time was the backgate, that the MOSFET is a 4-terminal devices. So I want to start using this as kind of a starting point. Then to use the angle, and then I'm going to answer 2 questions. Is that the why FinFET takes over something is because we are in the pursuit of fully depleted transistors. But there are several types of fully depleted transistors. And so I'm trying to do is that I'm going to use some model, then a theory aspect I'm going to peer through to distinguish the difference between these fully depleted transistors. And the second is I want to put in the context of FinFET in the scaling theory. So it actually has some kind of a role into the technology scaling. So with these 2 angles, I'm trying to accomplish today. So a little bit about history about fully depleted transistors. This is precisely the time I left Berkeley. There are several choices of fully depleted transistor at that time. There's a SOI MOSFET, and there's a ground plane MOSFET, and there's double gate MOSFET. So how things evolved 15 years later, during this time, SOI evolved into fully depleted SOI, then evolved into ultra-thin body SOI. And ground plane MOSFET actually joined force, the merged together is become the same. I think right now you look at the ideal structure, they are indistinguishable. It's just become a one class of structures. And the double gate MOSFET evolved into FinFET. So that's kind of how scientists, academia, and industry research, they study, and then they came up with these kind of evolution. So a little bit background that before I start to try to a bold attempt, try to dissect these transistors. So let's look at I only want to use 2 parameters. The first one is the drain-induced barrier lowering. So pretty much indicated by how flat these transistors, when they call saturate, when it's saturated, it's supposed to be flat. So it does not change, it's saturate. So a good transistor, a good diagonal transistor is very flat. A poor, then it keeps increasing. So that's one aspect. So a good one and a poor one. And also then another parameter is a good subthreshold slope. It's a good subthreshold slope is that very steep, and also they merge together. And a poor one is that when you apply a drain bias, then it starts to leak. So it starts to kind of spread out. So obviously, we want a transistor that saturates well with a very good drain-induced barrier lowering, and a very steep turn on, turn off is a good subthreshold slope. So now we revisit this. MOSFET is a 4-terminal devices. So how do we control the drain-induced barrier lowering is that we use the front gate and the back gate, so the 2 gates together to control the drain-induced barrier lowering. And how do we have a good subthreshold slope? It's actually the ratio between these 2 is determining the subthreshold slope. You want the front gate to be strong. You want the back gate to be weak. And so on one hand, you want both to be strong. On the other hand, you want one to be much stronger than the other. Okay, so if we start from this one, let's look at these transistor architectures. So the problem with the fully depleted SOI. The fully depleted SOI, first of all, is start with a partially depleted SOI, and then there is a electrically neutral region, and then later this structure, after you scale, it disappears and then becomes so-called fully depleted. So it has a very good subthreshold slope. People are very excited about it. But why is it so good? It is actually the front gate, back gate ratio is very good. It's because the back gate is very weak. So your back gate move from this terminal to that terminal. So you achieve a very good substructural characteristics. Not because backgate is good, it's because backgate is poor. So therefore that, if I come back to what I just pointed out, that then drain-induced bellowing cannot be too good because you need both gate to hold the channel together to fight the drain. And if you don't, then you can't. But this aspect actually was not revealed because the barium oxide does help. Because the punch-through path go through the substrate, but then if you have a very, very high barrier, then you don't see this current. I think this is part of the reason I think the people been very, even though this seems to be a problem, but it did not reveal in the first place. So, but then I think I had I remember that time I had some intense discussion with the professor about this one. And and also I think once I confirmed this, I think there may be just a week of time or 2 weeks of time, I was maybe a world-leading expert in knowing why SOI has a problem for a short period of time. And that is later than I joined IBM. I think this is going to be something that a tough situation to deal with. But I think this is probably a kind of a fundamental issue with this kind of transistor architecture. The problem with the ground plane, and then by this time you probably can relate this to, it has a very good strong gate of front gate and back gate. If you do it really as a ground plane transistor, the ground plane transistor has a very, very strong back gate. So the problem is now that the front gate to back gate ratio cannot be good because they both have to be very, very strong. And so I think I listed that if you need to have a maximum of front gate plus back gate, then you have to have a maximum of front gate over back gate. So in that case, I think the combination is that I think the solution is that you just put these two gates as one, and you get rid of the other. So that's what double gate is. Okay. Then the double gate FET, a good transistor. Okay, I just said that. So it has to go to double gate. The problem with the double gate is that its process is very difficult, and the parasitic capacitance is a tremendous problem. And so at that time, as I said, we were blessed to have a researcher, Tetsu Tanaka Fujitsu. He really came in and build a transistor and then cut it and flip it and bound it and do it again and make these double gate transistors. It's a very, very nice transistors, but the yield, of course, is beyond what is not doable. And so this one I cited Phillips' paper, and so during that time, I think there was three type of a double gate transistor being considered. Type 1 is a horizontal current flow. Type 2 is a kind of current going from the bottom to the top, and Type 3 is a gate on both sides. I think when Philip, you wrote this paper at that time, it's probably implicit that you put the Type 3 the last because you don't think that is going to happen. And we put in so much effort, and we don't think Type 2 is interesting because the current is flowing this way, the routing, everything is different. So we put in so much effort in Type 1. And it's a great effort. It's a heroic effort and Philip led a charge in IBM Yorktown. This is an amazing process that you build the horizontal transistors, and you cut a hole, you make a tunnel, and then you go epi through the tunnel, and you build this transistor, and you polish. And that's just how we are determined to make a double gate transistor. And, I think but the result is great. Philip now is a professor at Stanford, so I think it works out very well. Okay. And I think it turns out that Type 3 is what is really pan out in the end. And I want to mention also, I think at that time, under Professor Hu, there's a researcher, Toru Kaga, he also joined us during that time. So I think this is really, during all this early work, people are just thinking about building fully depleted transistors. But to identify this transistor as the solution for scaling, I think this is something as a truly have some foresight and insight. So the champion horse was identified at that time. So Next, I'm going to talk about, talked about the fully depleted transistors. Next, I'm going to talk about that really, how does FinFET fit into the scaling. I think I pretty much covered the how it fit into scaling in terms of device physics. And it's better scalable. But I want to extend that a bit more to the context of a power and how do we extend the Moore's law. Okay, so I'm sure in the audience, people, you're more familiar with than me about this one. I joined this industry pretty much in the later part of this curve. And so I just want to use this one as an introduction. So I go back to the original paper. And this is the original paper. I think Mr. Gordon Moore did some revision, changed the slope from double the component every year to double the component every 2 years. So then he went ahead to project that there's how many components that is going to be produced in a chip. So when Mr. Gordon Moore made that observation and then later being quoted that law, if you look it over, he just means that there will be many components in the chip, right? But it does not necessarily mean that transistors have to be smaller. It could be wafers getting larger. It could be anything. But then I think it's not necessarily has to be one formula. Then I think it kind of around the same time. I think okay. So when you start to put this component together, this has been a kind of a popular chart recently, just that if you keep projecting with kind of putting these components together according to our current trend, the power on chip will reach the hot plate, will get into like a nuclear reactor, and then will be a rocket nozzle, and then will be the surface of the sun, just in several generations. So, and I was with IBM, so we have a similar plot, but not as dramatic. So we actually project that bipolar is going to have a problem that we switch to CMOS, but CMOS will have the similar problems too. So this is really the issue that we try to deal with in terms of scaling. So, and the scaling theory from that aspect, even though I think some people use them, did not distinguish them, but this really are different. I think the scaling theory is that is observation that Bob Dinard did. And so this scaling theory actually helped when you put so many components together. You don't burn out. You don't go to the surface of the sun. It's actually when people deviate from this law, from the scaling theory, and then you have these problems. So look at these parameters. Look at the observations that okay, the power density will equal to 1, and then you have to adjust device dimensions, the oxide thickness, L and W. Okay, these parameters. And you also have to change the doping concentration. If you cite the original paper, this is 1974, the paper title is very specifically mentioned about implantation. So implantation was a great technology at that time. You can implant like ppm level of dopant into the crystal and then change this property from N-type to P-type. That's really great things. And so he observed these, under the, today we call it band edge metal, but it's N plus poly or P plus poly. There's a special relationship with oxide thickness and doping concentration. You can maintain that relationship and by following this law. So that was the scaling theory. And I want to really go ahead and talk about how does FinFET fit into this theory. So the traditional scaling is that, okay, we have the oxide, the L, and the VD, then we scale them into a particular fashion, then we can keep the power density equal to 1. And we can keep the performance, keep going ahead. So how does FinFET fit into this? It's actually, there was a precedent already, is that the traditional scaling is that this is the parameter. And high-k middle gate deal with this epsilon. Right? Okay. And FinFET, interestingly, you should look at it, it's really dealing with this parameter. And if you group these three together, and if you plug into these scaling equations, they are really indistinguishable mathematically. So you can treat them as one. So FinFET, what it does, it decouples. Go back to the previous page. It decouples. it decouples the design width with another width. So that was not possible in a traditional planar-like transistor. That introduced another parameters. And so what did this parameter do? It does the same thing as all the others. This is not a parasitic capacitance. This is the device capacitance that we scale up every generation. The scaling is about scaling up the capacitance. Of course, then later area per, then you say you keep that constant. But every generation, we want larger, larger, larger capacitance. So this term, getting here, it helps us scale up in order for gate control. Yes, it does gate control. It provides high drive current. Yes, it provides high drive current. And it reduces sigma BT. It does exactly the same, even though the formula may be slightly different, proportional to the square root of it or the first power of it. So this term actually enables us to fit into the overall kind of a scaling. And we may not be the direct, they'll call it Dennard scaling, but it's an equivalent scaling. Okay, so want to thank Clement for the great work. And so it helped us extend the Moore's law to 7 nanometer and beyond. That's what we believe. And also FinFET right now is a POR for TSMC in 16 nanometer node. And also we'd like to take this opportunity to express the university research is essential. It's a job security barometer with a 10 years forecast. So we really need that. And in this IEDM, I was really amazed to see that you can make this chip into a tattoo. Some of you were in the panel session. And even it's edible, you can eat it. I think the speaker on the front just eat one of his chips, showing everybody that this is safe. And and I look at that as a great opportunity because that should help us in terms of how to utilize those 8-inch volumes because we have to find some way. Okay, and when I was at Berkeley, people tell me this: if you build it, it will come. Of course, this is cited from somewhere else. As I get older, I really find that's the case. It is really true. So just keep building these things, and they will come, and we'll all benefit from it. Thank you.
I want to take a moment and acknowledge Wann as well as Philip. They were, in a way, competing, although there was no overt competition. We're just working quietly. We know IBM was doing great double gate work. There was effort everywhere. And so when we published this 1999 paper that everyone now talk about on the FinFET, it became suddenly an overnight media event, and a lot of comments and all that. They were all positive. But the one I really valued the most, above all, really is the one from Philip, because I knew that Philip understands everything, and he also has the intellectual power of Clement working with him. And Philip's told E! Times, he says, Clement has really found the answer. So that's the one that I really remember, and Philip is just wonderful. I think I repaid him by doing him a favor a few years later. I was already working at TSMC, and one day I got a phone call from Philip. Philip says, I've worked at IBM for more than 10 years. I think I want to change and move to a university, and now there's this university that is recruiting me, and what do you think? So my response was that, Philip, that university is not good enough for you. I suggest him to apply to Stanford, and there we are. All right, thank you.